Hey everyone, welcome back to another AP Calculus video. Today we're going to talk about how to find the area trapped between two curves. Now we should already be familiar with the idea that the area under a curve is found by integration. And so if we consider the two curves that I have here, and we wanted to find the area trapped between them from 0 to pi over 4, we want to remember that when I go and I try to integrate this red curve, so if I do the integral, we're going to call this one y1. The integral of y1 from 0 to pi over 4 is going to give us the area trapped under the curve, between the curve and the x-axis. So that's going to be this space right here. Now, if I go and integrate the second curve, we'll call this guy y2. And if I integrate y2 from the same limits of integration, it's going to provide me with this area. It almost looks like a triangle. It's not a triangle, it's a curve, but it looks triangular zoomed up close. And the idea is I can find both of these areas with an integral, but if I want the area between, what we want to do is we want to take the whole pink area, chop off the blue area, and that's going to be our result. So basically what happens is we're left with this idea that if I integrate from 0 to pi over 4, y1 is the upper curve minus that same integral from 0 to pi over 4 of the lower curve. And so once we have this kind of figured out, we can actually use the property of integrals and combine them and say, hey, it's the integral, we can turn it into one integral, 0 to pi over 4, the upper curve y1 minus the lower curve y2, and that'll give me the area between. And so now we have this kind of nice, easy way to think about what's going on. We can now use our graphing calculator and find the area between the two curves. Now when I'm using my graphing calculator to find solutions to problems like this, one of the tricks that I like to use is I enter each curve into y1 and y2 on my graphing calculator. And the colors are going to be reversed here, but that's okay. But basically it's going to be 1 over, and then when I put the cosine in, I want to make sure that I put parentheses around it and then put the square on the outside. And then for y2, it's just sine. So these aren't too terrible, but here's why I like it. I don't even have to look at the graph here because I have the graph on my screen. And basically what I can do is math 9, type in my limits of integration, 0 to pi over 4, and then using the alpha trace button, I can recall y1. Just make sure that you remember which one is labeled, minus alpha trace, and then y2, and then dx. And so I can just type them in like this and get my answer. 0.707 is the area between those two curves. So basically, this is kind of what we've come up with. To find the area between two curves, first of all, both curves do need to be continuous. If they're not continuous, then we struggle a little bit. We might have to treat it a little differently. But provided that they're continuous on the closed interval, if f of x is the upper curve and g of x is the lower curve, then we write it like this. We say f of x is greater than g of x. The one that's lower on the graph, so remember you always have three ways you can consider functions: a graphical image, an analytical equation, or a tabular representation. That means numbers in a table. So here we have the analytical, f is greater than g, and the graphical would be a visual of the g, the one that's less, would be lower. So lower is less. And most of the time you'll have a graph, or you'll have access to a graphing calculator to be able to find the graph. But basically the area between would be the upper curve minus the lower curve, and the integral of that evaluated from a to b. Now this is great if you have a function that looks like this, where you have an upper curve and you have a a lower curve, and they stay that way, right? And you're given this area. But we're going to see here very soon. We'll try an example here together of one more of these. But what happens when you have an issue like this, where you have a curve and then you've got a curve that kind of comes down like this, and you want both of these areas and they switch places. So it's really critical that we make sure we pay attention to the graphs as we're going so we know which one is the upper and which one is the lower. And sometimes if they switch places like this, we may have to break up our interval and do two separate integrals because the upper and the lower switch places. So we need to accommodate that. And we're going to see that here in just a few moments. But first, let's take a look at another graph. And so we have the area between these two functions. And here's what the graph looks like. And I'm going to make sure that I have these put in to y1 and y2 on my graphing calculator. And so here is what it looks like on my graphing calculator. I've put everything in, and I'm just going to real quick make a note. I labeled this y1, it's my blue curve, and this one is y2, it's the red curve, it's the line. And oftentimes if you're given functions and you're shown the graph, it is up to you to be able to determine, hey, this is the parabola and this is the line. So that's an expectation of you. But now we want to find the area trapped between these two curves. So that means we need to find the intersection points. So this one I'm going to have to find the intersections of. Now suppose that I don't have a graphing calculator and I need to solve them. I'm going to kind of demonstrate how you would approach it both with and without a calculator. So for this one, to find it with a calculator, we'll go ahead and find one of the intersection points. We have to go through this process twice. So second, calculate, and we're going to go down to option number 5, intersect. It's going to ask us for the first curve and the second curve, and as long as you only have two curves in, you just hit enter, enter, and then get that cursor close enough, and you get -1, 1. So that's going to be one of our points here is -1, 1. So we have -1, 1. And then to find the other one, if we wanted to solve this not using our graphing calculator, we would solve it in a different way. We would solve it using algebra. And so the algebraic way to solve this would be to take the two equations, 2 minus x squared equals -x, and to set them equal to each other. So you'd have to factor, so get 0 on one side, x squared minus x minus 2. And remember, I got that by subtracting 2 and adding x squared. So plus x squared minus 2, and then rearranging the terms. And then I'm going to factor into x minus 2, x plus 1. So this is where x equals -1 is a solution, and then here x equals 2 is my other solution because I'm setting that equal to 0. So this is a reasonable problem to be that you would be expected to do without the use of a calculator. So let's continue, and we'll do our setup. We'll do it without a calculator, and then we'll check it with our calculator. So the upper curve is y1. So the integral that I'm going to do is from -1, so the x coordinate, to +2, and then y1 minus y2. Now this would be a sufficient setup if you were using a graphing calculator. This is all you would have to show in order to solve this problem with a calculator, and then you would spit out the answer because you would do the calculations in your calculator. But here I'm actually going to do this by hand. So -1 to 2, and y1 is 2 minus x squared, and then minus -x dx. And as I simplify it out, -1 to 2, I'm going to have 2 minus x squared plus x dx. So the antiderivative there is going to be 2x minus x cubed over 3 plus x squared over 2, and we're going to evaluate that from -1 to 2. And yes, we're doing quite a bit of work here. So as we kind of work it out, we're going to have 2 times 2 minus 8 over 3 plus 4 over 2. Oh, minus 2 times -1 plus 1/3 plus 1/2. Boy, this is not a pretty answer. Minus 8/3 plus 2 plus 2 minus 1/3 minus 1/2. So this is going to be 9/3. So 4 minus 9/3 when I combine these two up. Let's see, plus 2, that's 4 plus 3.5. And I'm going to write it as 7/2. 4 minus 3 is 1. 1 plus 7/2. That's 3.5. That's going to be 4.5. That's going to be 9/2. or 4.5. So that's the answer that I would get just doing this by hand. If I wanted to evaluate this using my graphing calculator, here's what it might look like. I would use Math 9. Math 9. I'd go -1 to +2. I would just type in alpha trace y1 minus alpha trace y2 dx. A little faster than doing all the calculations by hand. 4.5, and there you have it. You need to at least show the integral and the setup that goes with it in order to get full credit on the AP exam for your response portion. Now, as we consider this next example and getting it into the graph and taking a look at it, there is a problem with this one with trying to find the answers, because we want the area bounded in the first quadrant between these two curves. So just looking at the graphs, here's the area we want. Now, let's kind of think about this. If I were to do the integral of the blue curve minus the red curve, from 0 to, this looks like 4 maybe, so 0 to 4, and we'll confirm that it's 4 in just a moment. If I do this area, what that's going to do is that's going to provide me not only with the green area, but it's also going to give me this other area underneath. And so I'm going to have more area than I want. I don't want this area. And so this is my problem. And so for this kind of an issue, this is an example of where we might have to split our integral and figure it out using a split integral. So let's take a look at what's going on with my split integral and make some decisions about this. And we're going to do this without the use of a calculator. We'll confirm it with our calculator, but let's remember we don't want this. And so if I were to split this integral, I would have to split it right here. Now, what is this spot? Well, on the graph it looks like x equals 2, but let's be sure. So this is the red line, so we're going to call this one y2. And then we have our blue line, we'll label this y1, that's the square root function. And so where does y2 cross the x-axis? Well, that's going to be where 0 equals x minus 2. So sure enough, x equals 2. So this is the spot x equals 2, and then this spot right here where they intersect is another key point that I need to find. So let's go ahead and find that. That's where y1 equals y2. So that's where I'm going to solve the square root of x equals x minus 2. And to solve this one, I'm going to have to square, or if I, this one actually I can probably figure out that x will be 4. So if x looks like 4, instead of going and solving it out, if it looks like 4, then let's see if it's 4. Square root of 4 equals 4 minus 2. Oh, 2 equals 2. It is 4. So I don't have to always solve. If I know what it looks like, I can just check it out, and if it works, it works. Great. Save some time. So here's what I'm going to do. I'm going to integrate this blue curve from 0 to 2. And that's going to give me this area. And then what I'm going to do is I'm going to do a second integral, and I'm going to go from 2 to 4, and this is where I'm going to do the blue curve, square root of x minus that lower curve, x minus 2. And then if I add those two values together, that'll give me the entire area. So let's go ahead and do this. This is x to the 1/2, so when I integrate, it's going to be x to the 3/2 over 3/2 from 0 to 2. It's going to be 2/3 x to the 3/2 from 0 to 2. Well, the 0 is easy, so when I put in 2 cubed is 8, so I'm going to have 2/3 times the square root of 8. So that's going to be 4 square root of 2 over 3. And then when I evaluate this one, I'll go ahead and use a calculator just to save a little bit of time. The antiderivative would basically be this, essentially, plus a couple other things. And we'd evaluate that from 2 to 4. And I can already tell this is going to become a little bit longer than maybe what I want to do by hand. So let's go ahead and make that adjustment. Here's y1, here's y2, and math 9. Let's try that again, math 9. And we'll go from 2 to 4. Alpha trace y1, the upper curve, minus y2, alpha trace. Oops. Let's try that again. And there we go. Alpha trace y2 dx. So I get this decimal, and then I'm going to add to it. Let's go ahead and let's double check that integral from 0 to 2. This one's just y1. So alpha trace y1 dx. And I already added it in, so 3.33333 repeating, probably 3 1/3. But we'll go ahead and just kind of round it to 3.3 repeating, or 3.333, since technically I guess it's not repeating, so let's not dig ourselves into a incorrect answer here. But this would be how we'd want to approach this. And so being able to evaluate these both by hand and by calculator is a really important skill to have, and recognizing when we have to split it, because we only want the area in the first quadrant. Recognizing that that is a problem. Remember, when you just do the subtraction, it's going to give you all of the area between. If you don't want all of the area between, you have to take it easy and split your integral. So let's take another look at another way we could have solved this problem. And splitting our integrals is fine, but if we take a look at this graph again, and let's see, here it is. If we take a look at what's happening on this graph, we could think of it in a different way. And the way that we could think of it is by rotating our graph. And so suppose instead of thinking about it this way, suppose we thought of it in terms of, well, what if I rotated it and I had my curve like this? There's my square root function, right? So my x-axis becomes the y-axis, and then I have this square root function. That's not a very good square root function. It kind of goes like this, and then your red curve kind of goes like this. What if we thought about it this way? And put x up here and y down here. And this time now, it's like, oh, wait a second. Here we don't have to split our integral, because we still want this area. But now, instead of thinking about it as an upper curve and a lower curve, now if we think about it as a right curve and a left curve, well, the curve on the right would be our upper curve. It's the greater curve. And the curve on the left would be the lower curve. Left is lower, right? And so if we think about it this way, we could integrate instead of with respect to x, with respect to y. And so it looks a little bit something like this. The area between the curves, we can consider it as a function of y. And so here, this becomes the right curve, and this becomes the left curve. So they're going to switch places. The one that was on top with our dx setup is now the lower curve when we do a dy setup. And in order to do a dy setup, we also need to rework our equations. So where we had y equals x minus 2, we're going to need to solve for x. We're going to get x equals y plus 2. And in the same way, when we had y equals the square root of x, now we're going to square both sides and get x equals y squared. So we need to consider all aspects of rewriting this in a dx format into a dy format, and we need to solve for x equals. And so now we have functions of y. This is what it means when we say f of y and g of y. It means we have x equals, and y is now our variable. They've switched places. And so our setup here would look a little different, and we would do this. We'd say the integral, and we'd choose the y values. We'd say from 0, or sorry, I guess it isn't. Yeah, it would be from 0 0 to whatever this is. So if this x was 4, then y is 2. So we'd go 0 to 2. We'd use y values as my limits of integration. And we'd go from 0 to 2 to get this space in here. So it would be the right curve. So you would have y plus 2 minus the left curve, y squared, dy. So this is the right curve, and this is the left curve. It's the greater curve minus the lesser curve. The one on the right is the greater. And if we were to plug this into our calculator, it would look a little something like this. And I have to kind of rework it to make it make sense. I would go math 9, and since I don't have these in my Y1 screen, it doesn't make sense to do it when I'm doing this dy setup. I'm going to put parentheses around each function, and instead of y, I have to use x. So x plus 2, parenthesis, minus, oh, and I don't know why I said y2 here. This should say y squared. There we go. Minus, and instead of y, I have to use x. So the variable squared and then dx, because that's the language that my calculator speaks. And I should get the same exact answer. And it is 3.3 repeating. That's a fair assumption, I think, based on this. But you get the same answer, 3.333 or 3.3 repeating. And if we were to evaluate this by hand, we would get the same answer. This antiderivative is actually easier to find because it doesn't have that square root floating around, and you're only doing one integration. So if when you turn your graph counterclockwise and the right curve becomes the upper curve, and it appears that nothing is split, it's simply upper minus lower. The upper curve remains the upper curve, the lower curve remains the lower curve. Provided that happens, you can change your setup, and if it's easy to solve for x equals, you can use this dy setup instead of a dx setup. Now let's look at one more example here. Not this one. Okay, so as we wrap up, we'll end with this example here. And this example asks us to write but not evaluate an integral to find the area between the two curves. So as I kind of zoom in, here's the dilemma that I have. When I graph the two curves, the area trapped between them is this area here, and up here the blue curve is above. Over here the red curve is above. So I want to add these two areas together, which means I'm going to have to evaluate two separate integrals, and I'm going to have to split them. Now, if I rotate and try to do a dy problem, the setup for this, number one, I can't. It's not going to be helpful for me because it's not clear there is no right and left curve. The other indication that a dy setup is bad is I can't solve the first equation for x. It's a cube function, and it's just, no, I'm not going to. So let's go ahead and set this up. Now, I've already went through and using my calculator found the intersection points for these. And oftentimes you'll either be given the function intersection points if it's, you know, intense like this, or if it's a simpler problem that you have to split the integral for, you'll be given the graph, and finding the intersection points will be fairly simple. So let's go ahead and start. I'm going to, for the sake of ease, label this y1. Always label your functions. We'll label this y2. That way we know blue and red, it matches up. So my first integral is going to be to find this space right here. So let's go ahead and set that up. So I'm going to integrate, and I need this left intersection point. Well, that's this value right here, negative 2.114908. And oftentimes we can say let A equal or let B equal. So if you label it A and you label this one B and you label this one C, then in your integral setup, as long as it's clearly labeled, you can just say from A to B. That's fine. That's perfectly acceptable. I'm going to go ahead and put the numbers in, and I'm going to make sure that I go out to as many places as I can to ensure my accuracy. So then 0.2541069. So that's going to give me this first area, and it's going to be the blue curve, y1 minus y2 dx. And then I'm going to add to it the integral for the second space. So that's going to be this one right here. So we'll go from 0.2541069, that's that center point, all the way to this C point, 1.860859. And here they switch places, so I have to make sure I put y2 minus y1 dx. And if I add these two together, whatever the result is, that's the integral setup that I would want to use. So the important thing here is that when you are doing these problems and setting up to find the area between two curves, you always want to picture the curves and make sure that there's no overlap like in a problem like this, that you don't need to split your integrals. The other consideration is to always think about, is there a better way to set up my integral? Can I set it up using a dy? And remember, we can use dy when there's a clear right and left curve. In the example we just did, there was no clear right and left curve. So here, there was a clear right and left curve. So when I look for the upper and the lower and think about them right and left, it was very clear. And then I just use all y values. So that was easy enough to set up. And you also have to make sure that whatever functions you're using, you can solve them for x equals. You can't always solve them for x equals. So dy sometimes is an option, but sometimes it's not. So as you're doing these, the best way to get good at them is just by practice. And the more practice you get, the more proficient you will become. So don't expect mastery at first. It's a work in progress, and just keep going. You can do it. You've got this.